Welcome to Music 320, week 10. This is the first lesson, digital delay using tap in and tap out. So first I just wanted to go over the theory of a digital delay. Essentially with a digital delay, you need a device or an object that will store a certain amount of audio. In this case, in this example here, I'm imagining this to be a vertical tube where samples are stored, and the size of the storage is 2,000 milliseconds. So there's enough room to store 2,000 milliseconds worth of digital audio samples. Essentially what happens, in theory, is that data is stored in this buffer, and as new samples come in, the samples that have been there the longest, essentially you can think of them as dropping out the bottom. So the buffer always contains the last 2,000 milliseconds of sound. Now, in order to get a digital delay, what you do is you pull the data out of this buffer at some point along some point in time. So that is sometimes called the tap point. So if we have a tap point here, we're essentially pulling the samples out at this point in time. And this really will be the sound 500 milliseconds after it first was put into this buffer. If we move this tap point down, then we have sound that has been stored in the buffer longer. And if we move the tap point up, we're getting sound that was stored less time. So we have what you would call it would be a shorter digital delay if we move up. So that, in essence, is how a digital delay works. In terms of how it's actually implemented, the samples don't fall off the bottom of anything. It's usually implemented with a circular buffer or an object like that, which simulates this idea of the data, new data coming in and old data being lost. So let's look at the max implementation of this. The max implementation uses two objects, a tap in tilde object and a tap out tilde object. So let's start with the tap in tilde object, which takes one argument, and that argument is essentially the buffer size, or the maximum size, maximum delay time that we're going to use in our system. So essentially this just means that I have a tap in tilde and it's got room for 2,000 milliseconds worth of audio. I can take my samples out of that buffer anywhere between 0 and 2,000, but I can't take them out past 2,000 because they don't exist. And I'm going to hook that microphone into the tap-in object. The next object is the tap-out tilde object, and it takes as its argument the delay time, or the place in that buffer that we're going to pull data out. Now, I'm going to connect these two together. Now, the tap-in, this is not actually a signal connection between the tap-in and the tap-out. It's really just a logical connection to show, so the tap-out knows which tap-in it's going to be drawing values from. If I were, for example, building a reverberation system, I might have many tap-out objects all connected to the same tap-in, so that a signal would come in and I would have many delays trying to replicate a space where sound is bouncing off objects and bouncing off walls and so on. But here we're just going to do a straight single digital delay. So let me connect the tap out to my output, and we should get a single 500 millisecond digital delay. hello, 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 hello. Okay, so that's working perfectly well. Now, the other thing that we generally have in digital delays is a repetition of our delayed signals. And so in order to achieve that, what we need to do is we need to add a multiply tilde, and we are going to take the signal that comes out of the tap out, and actually I'm not going to make it 1.0, I'm going to make it 0.5. In fact, we don't want to put the entire signal back in because it'll start accumulating in volume. Generally, we want to go somewhere around 0.5. That would mean that half the amplitude of the signal is then passed back into the tap in so that it can be repeated again. So every time we go through this loop of the tap out multiplied by 0.5 going back in, the signal will be reduced by half of its amplitude. So we'll get a kind of an echo effect at 500 milliseconds. So let's hear what that sounds like. Test, 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 test. Okay, so we could put a floating point box in here, and we could attach it into our multiply tilde. One of the things I'm going to do right away is go in and set my minimum value of that float box to 1 and my maximum value to, let's say, 0.95, because I want to ensure that I never get values that are 1 or even close to 1, or I'll just start overloading the amplitude of my output. Okay, so we can see what happens, for example, then if we have a value of 0.8 in here. Well. So you can see what happens. Okay. All right, so there's our basic digital delay. We can change the frequency of the digital delay, and we can change the basically the time of the digital delay, how long the gap is between each of those repetitions, and we can change the feedback level. So let's start with another floating point number in here, just to hear a little bit of maybe some different delay times. Let's put in 200. Okay. So that sounds a lot more like reverberation. It's very hard to talk while you're hearing your digital delay. So 200 is obviously a lot shorter period of time, and if we want a really long sort of digital delay, we can put it at 1500, and that will sound like this. So you can hear the delay of 1500 milliseconds. Okay, so next what we're going to do is we're going to put a control on the frequency change. Essentially, I mean, the way to think about this is in that diagram, we have that tap position. We're going to kind of fluidly move that tap position around. And so rather than using a floating point number like this, I'm going to use a line tilde. And the line tilde, as you remember from other times we've used the line, essentially will give you sample rate adjustments to values. So this will be a perfectly smooth way of adjusting that tap point. And let's put a message in like move to the new value in 100 milliseconds. So it sort of slides around a little bit. Now, one of the things that happens, there's a kind of an artifact here that when we're sliding around that tap position, it's a little bit like a Doppler shift occurs, because as we move that tap position further down or to larger time values, the pitch will start to drop. And that's because the samples are sort of getting stretched out. They're getting separated from one another as we move that pointer down. And as we move the pointer up, again, kind of like a Doppler shift, the samples will get pushed closer together as we move it up. And so we will temporarily hear a pitch shift upwards. So let me put a floating point number back in here. And you'll hear what I mean as I start to change these values around. Let's start with 500. Okay. Now I'm going to start moving this around. And you can hear the pitch is getting altered. So as I move it down to lower numbers, then you can hear my pitch getting higher. And as I move it up, the pitch gets lower. And here it goes. And the faster I move it, the more dramatic those changes are. So you could imagine, putting a line on this and sort of randomly changing the delay time to create a kind of, strange pitch shifting digital delay unit. If you don't want the pitches to shift like that, if you don't want, then don't use the line object. But just be aware that you may get some slight glitches or clicks when you try to discretely change the tap out time. So as I mentioned before, if you wanted to build a more complicated digital delay system, you can certainly have more tap out objects. You generally don't have more than one tap in a unit like this, since it's kind of recording the same information. It doesn't really get you any advantage, but you could certainly have 2 or 3 or 4 or 5 or 10 or 12 tap out objects, each with different delay times and possibly even each with different feedback levels. So let's do some crazy stuff with this to finish off with. I'm going to put my delay feedback up to like 0.75, and then I'm going to start playing with this. And you can hear that this is kind of strange. Getting a kind of strange, distorted, digital delay. Okay, so that's week 10, part 1, and I'll follow this up with a look at digital filters.